Hello everybody, welcome to the lecture of Scalable Data Science. Today's lecture is on frequent elements. So before we start the lecture, we'll just revisit the streaming model that we have been talking about. In this model, we are seeing data as an incoming sequence, right? And this sequence could either be element IDs. For instance, you could say that we are getting ID A, we are getting ID A or ID B or ID C, ID A prime and so on. Or you could have a model in which you say that okay, instead of just getting the ID A, we get the ID A along with an update to the frequency of ID A. We get the ID B and along with that an update to the frequency of ID B and so on. Right? These are two models that we sometimes use interchangeably. As you can imagine that the second model, the update model, is a little more powerful. Right? So there are two types of streams that we typically consider. The one is arrival only stream. Right? What that means is that either you are getting the IDs only, which effectively means that the update frequencies are 1 every time. Right? Or if you are getting updates, you are getting positive updates always, or at least non-negative updates. That is, you are never facing a situation when you are having to delete an element. The next, the most powerful model, however, is when you can combine both arrivals and departures. Okay? And such models can arise, for instance, if you are measuring fluctuating quantities. Right? So imagine that the price of a stock, right? You sort of at every day or every second you might be getting an update to the current price of the stock, right? And this could be so your stream could look like an ID of a stock and the update to the price, right? And then this update is can be both positive and negative, of course. Okay. So this is also known as the turnstile model sometimes, because the picture that you have in mind is that you have the turnstile in front of the through which people enter the metro stations, or maybe sometimes the train stations. So sometimes people could be going in, the turnstile turns right, sometimes people could be going out, the turnstile turns to the left, right? In most cases, we will deal only with streams when deletions can be made to objects that you have already inserted, right? Which means that the effective total frequency of any particular object or item can never go below 0. Okay? So this is also sometimes called the strict turnstile model. However, this is the typical case that we will be dealing with always. So unless I sort of say otherwise, we are always in the, whenever I say arrival plus departure, we are always in a strict arrival plus departure model, in which you are getting both positive and negative updates, but the negative updates can never result in the total frequency of any item being less than 0. Right? So most of our work will be in this lecture will be in the arrival only streams. We will touch upon the arrival plus departure streams in the next lecture. So the problem that we tackle in these two lectures, today's lecture and the next lecture, is the question of estimating frequencies, right? So in some sense, so here's the question. That suppose, imagine this is a stream. You get the red ball, you get the blue ball, you get two red balls, you get a turquoise ball, you get a blue ball, and so on, right? And at the end, you have to answer the question that given a particular color, how many balls have you seen for that color, right? For instance, if I give you the color turquoise, you have to say that I have seen 2 balls of this color, or red, I have seen 5 balls of this color, right? So in some sense, you have to create this histogram, right, which I have sort of pictured as a bunch of buckets, right. So, why is this a useful question first of all? So, this, I mean, as you can imagine, this is obviously a very basic question that you need to answer in most data analysis tasks, right. A very sort of common use is when, again, bringing back our example of network switches. Suppose you are designing some basic analytics tasks to be run on network switches, and one of the most common things that you could try to detect is whether there is a denial of service attacks that is happening, whether there is a denial of service attacks that is happening. Okay. So, and how would I detect that? Well, we could always track which are the IPs that are getting the most number of packets, right, in maybe in the last few seconds, maybe in the last 1 hour, right, and that could form part of a machine learning pipeline or data analysis pipeline that goes to predict that there is potentially a denial of service attack that is being built up. Okay. Another common use case is in database optimization. So, as you might already know, I mean, if you have a bunch of complicated joins that you are doing in databases, right, sometimes it makes sense to get an estimate of the various relation sizes after each of these joins, right, so that you can optimize this join pipeline. Okay. And if the databases are huge and they are stored in disks or in tape drives, then it's very useful if you can do one pass over each of these data sets and then get some estimate of the frequency of different element types of the different elements. Okay. Yeah, you could also imagine that if you are a huge web company, right, imagine you are Google or Yahoo or Microsoft, right, and you are trying to find, okay, I mean, from msn.com which are the most popular pages that are being clicked. So, you look at the website logs, right. Well, those machines they do not have a lot of memory to devote to your analytics tasks. So, you have to do things in very small memory, but you could try sort of building the kind of data structures that we'll talk about in order to find out that for today's visits, these 10 websites that are linked from msn.com are the most popular web pages, or are the web pages on which the Microsoft visitors clicked on the most. Also, it is not a surprise that these questions are used in subroutine in many other problems. For instance, in estimating the entropy of a data stream, right, in doing frequent item set mining and so on. By the way, the slides that you see today are courtesy of Graham Commode, and there is a link to a set of slides and the lecture notes at the end of the class. So, let us see what are the let us try to formalize what are the questions that we can try to ask about this frequency estimation. The first question is this, that okay, what is the best I can hope for? The best I can hope for is that, can I create a data structure, right? Let us call that a sketch for now. Can I create a data structure or a sketch that is sublinear in the size of the data, right? Because if I were to use space that is linear in the size of the data, I can always use something like an array, right? Something like an array and associate set of counters. So, that is trivial. So, can I use a data structure that is sublinear in the size of the data, right, and can answer all frequency queries accurately, which means that if the number of unique IDs is n, what you want is a data set is a data structure that is small o of n, right. Is it possible to do this? Unfortunately not, right. It is not hard to say that, I mean, again using information theoretic arguments, that you cannot hope to design something that is small o of n in space and that answers all the frequency queries exactly. Okay. So, that is gone. Okay. Let us come to the next question. So, instead of trying to answer all frequency queries, sometimes the issue is that maybe there is a huge number of tail queries, of sort of tail elements, right, which are very small frequencies. And the question then is, can I, so suppose I do not worry about them, suppose I only worry about giving accurate answers to the most frequent elements, okay. Can I do this? So, I could certainly do this if in the offline setting, right. For instance, if there are only let us say 10 frequent elements, 10 elements which are most frequent, and I am not defining this most frequent very accurately right now, very precisely right now. Suppose there are 10 elements which are high frequencies, everything else is low frequency. So, in sort of one pass over the data, right, I could maybe try to guess one of these elements, right, or basically if it's offline, then I could always sort, right, and then find out which are the most frequent elements and then only store the frequencies of this, right. However, we cannot really do this again, right, as you already see from my answer, because once you try to sort it, you are already using linear space, right. So, even this is not really doable in sublinear space, right. So, when I say not really doable, it is a combination of sublinear space and one pass. Okay. So, in one pass sublinear space, the first two questions that we are trying to answer are not possible. Okay, let us come to the third question, which is a relaxed version of the first two. Can I try to approximate the frequencies of the most frequent elements? Okay. If I cannot answer them exactly, can I try to give the answers approximately? Okay. And I am not even making precise what approximation really means, right. So, we will come to this, and it turns out that yes, for certain definitions of this approximation, it is possible to do this, right, and even that turns out to be a non-trivial question to study, which is, and that is what we will study in this lecture and the next one. Okay. So, let us try to define what we mean by approximation. So, by the way, this particular problem, the question of finding out the frequency of the most frequent elements, has various names in literature. It is called heavy hitters, it is called elephants versus mice, and so on. And they all really are talking about the same problem. Okay. So, let us see, let us try to define it this way, that suppose we have an update stream of length m. Okay. Remember that we are always talking about, and at this point we are talking about a universe whose size is n. So, there are n distinct elements. Well, we could even do a little better. We could say that the universe is big, but the number of distinct elements that you see is n. So, n elements, right. But the length of the stream m is bigger than n, right, because an element can come multiple times. So, given an update stream of length m, find out all elements that occur frequently. So, let us say by frequently, I mean that it occurs at least 1% of the time, okay, which means that their frequencies is at least 1% times m, right, 0.01 times m. Okay. Unfortunately, this cannot be done in sublinear space one pass. So, you cannot find out the set of all elements, that the exact set of all elements that appear 0.01 I mean 0.01 m times, right, in space that is sublinear, right. And while I am not giving you the proof, the intuition is this, that when you see an element the first time, you have no clue of whether it is going to be it's going to become one of these heavy hitters or not, right, or one of these most frequent elements or not, right. And you have to keep it, and therefore you have to keep around these elements in order to, because if you don't keep it around, then you're never going to then you miss its frequency, right. So, it's possible to design sort of formalize this intuition into a concrete proof, and this was the question 2 that we had asked. So, the version of question 3, the formal version of question 3 that we will now try to tackle is this, that suppose, can I do this, right, that can I give a guarantee that says that we will find out all elements that occur at least some phi times m. So, this phi was 1% there. So, think of phi as some number between 0 and 1. Okay. So, what I want to guarantee is an algorithm, what I want to give is an algorithm that guarantees that all elements that occur at least phi times at least phi m times are there, and none that appears less than phi minus epsilon m times are there. For epsilon, that is between 0 and phi. Okay. So, epsilon is the error. So, remember, so see that there is a gap here. While we are guaranteeing that all elements at least phi m whose frequency is at least phi m will be there, right. I am also guaranteeing that all elements whose frequency is less than phi minus epsilon will not be there. For the things in the middle, for the elements whose frequencies are between phi m and phi minus epsilon m, I am not guaranteeing anything. Okay. So, this gives me the slack to work with. So, epsilon is the error. A very related question, and one that we will tackle will actually tackle in this particular talk, is to estimate each frequency, right, with error plus minus epsilon m for some other epsilon. So, do not think of this epsilon and this epsilon. Well, you could think of these two epsilons as being the same, right. What we will say is that if the actual frequency of an element x is f x, will give you some f hat x such that f x is not too different, f hat x and f x are not too different, right, which means that they somehow differ in as plus minus epsilon m, right. And this statement again is not formal. The exact form of the statement will depend on the algorithms that on the particular algorithm that we will give, but this is more or less what we want to do. Okay. And this is the version of the question that we will actually tackle. So, let us start with a puzzle before we give the algorithms. That suppose we have a set of n numbers, and this puzzle was posed by J. S. Moore in 1981 in the Journal of Algorithms, and he posed it in the setting of a distributed computing, but it's valid nonetheless in other settings also. Suppose we have a list of n numbers, and these n numbers represent the votes of n processors on the result of some computation, right. So, maybe the processors they have had slightly different inputs, they have had slightly different randomness, and they are all saying, and they are all giving a vote on the result of this computation, right. And let us say the votes are is a particular number. So, let us say the vote is number 1, number 2, number 1, number 3, number 1, number 1, number 2, number 3, number 4, right, and these are the votes, right. Okay. So, now he is asking that is there a majority vote, right, is there a strict majority vote, that is if there are n processors, is there a particular option that appears strictly n by 2 times. Okay. Here for instance, you could potentially say that maybe if I put in a few more ones, the option 1 appears bigger than n by 2 times. Okay. So, this is easy to do as such, right, because you just you can just keep a counter and so on. But again, can we do this? Can we answer this question in sublinear in n space? Okay. So, it turns out that his setting, the setting that the puzzle was asked in, did not really sort of talk about streaming, because streaming was not formally defined as a model as of then. But the solution that he proposed is actually a streaming algorithm. It is actually a streaming algorithm that uses constant or logarithmic amount of space, right. So, it is pretty interesting, and let us look at the answer to this puzzle. Okay. So, here is what we want to do, right. Again, I am not giving the exact, and I am sort of casting the puzzle in our streaming model where we are talking about arrivals only. Okay. So, suppose we have this stream red, blue, blue, red, blue, red, 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 blue, red, red, yellow, there is no yellow, turquoise, blue, blue. Maybe I should put in a few more colors. Maybe I should have a pink out there. Maybe I should have a yellow out there, and so on. Okay. Okay. So now the question is that is there a just to make sure that there is a strict majority, I am putting in a few more reds. Okay. So now the question is there a sublinear solution to the question of trying to pick a majority item, right. So, here is what I want to guarantee, right. I want to give you an algorithm, right, that is going to have the following guarantee, that it is going to use only small o of n space, right. In fact, it is going to use only logarithmic in n space, right. Oh, just an aside, I mean typically what we assume is that n and the length of the stream m, they are related as polynomials of each other, right. So, when I say logarithmic in n versus logarithmic in m, they are basically the same thing, right, with the difference of constants. And it is useful to remember this because I will keep on interchanging, sometimes it is useful to state it in terms of logarithmic in m, sometimes it is useful to state the boundary in terms of logarithmic in n, but I mean that is the setting that we mostly deal with. Okay. So, coming back to the problem, right. So, can I give an algorithm that uses log n space, right, and that has the following guarantee, that if there is a majority counter, that if there is a majority item, you will have it in hand, will identify it. Right. However, if there is no majority item, right, and this is the slack, if no majority item, right, then the algorithm is not giving any guarantees, no guarantee. In fact, then the item that it has at hand, it will have at hand, might be a completely random item, might be a pretty bad item. Okay. So, there is nothing we can say about this. Okay. So, but of course, if we were allowed to do one more pass over the data, right, and this we are going to do only in one pass over the data. If you were allowed to use one more pass of the data, you can do away with this restriction, right, because once you pick an item in another pass over the data, you can sort of say that okay, this item is really a majority item or there is no majority. You can distinguish between these two cases, right. So, in one pass we will not be able to do that. So, what is the algorithm? This sort of mysterious algorithm. It is very simple. What we will do is that we will have a counter, right, a single counter that starts at 0. So, the counter will start at 0. So, for every item, so if the counter at 0, right, and you are seeing an item, you pick up that item, right. So, the counter at 0 we see red, so we pick up red, okay, and increment the counter. So, counter becomes 1, right. Next, then we go to the next item. The next item is also 0, is also red, right. So, I have the item red in hand and the counter is 1. So, because the item that I see next, which is red, is the same as the item that I have in hand red, I increment this counter, right. So, if the new item is the same as the item in hand, I increment the counter. So, I always have two things in my hand, an actual item ID as well as a counter value, okay. But then I see blue, the next element, and this blue is not the same as the red. So, what do I do there? So, I do not satisfy the first if, I do not satisfy the second else. So, I come to the last else, which means that I decrement the counter. So, if the item that I see is not the same as the item that I have in hand, I decrement the counter. So, this becomes 1, but then I throw away the blue, then I get a red. So, then I increment it to 2, then increment it to 3, 4. So, it gets incremented to 4, then I see a blue, it gets decremented to 3, then it again increases by 2. So, it becomes 5. I see a blue which is different from red. So, it gets decremented to 4. I see a turquoise which is different from red, it becomes 3. I see a red again, it becomes 4. I see a blue, it becomes 3. I see let us say a red, it becomes 4. I see a yellow, it becomes 3, right. So, at the end I am left with an item red as well as the counter value 3. Okay. So, now what is the guarantee that we have? So, it is pretty clear that this is log n space, right, because we only are storing two things, an item ID as well as a counter value, and the counter value can at most be log of m, right, which as we said is again log of n, because we are dealing with polynomial size streams. So, the proof is surprisingly simple, right. So here is the claim: if there is a majority item, it is in hand, it is there with the algorithm at the end, right. So the first step is very important. If there is a majority item, we have it in hand. I am not guaranteeing you anything if there is no majority item. And why is true? It is fairly simple, right. So think of when are we dropping a majority item, right. So when you sort of when you delete, when you throw away an item, right. So remember, at some point we are at some, I mean, if the counter value is 0, we are dropping the item that we have in hand and we pick up the new item, right. If I decrement the counter, that is the same as dropping one copy of the item, right. So now, how many times can you drop a majority item? Okay. So each drop of the majority item happens because of one other occurrence of some other item, right. Because the only time that we drop an item is when we get an item, another item, and that item does not match the item that I have in hand. So each drop of majority item can be charged to the arrival of one other copy of another item, right. But the length of the stream is capital N, and there are capital N by greater than capital N by 2 majority items. So the number of other occurrences of other items is strictly less than N by 2. So therefore, you cannot account for all the all the majority items being dropped, all the copies of all the majority items being dropped, right, because less than N by 2 arrivals cannot account for greater than N by 2 copies of the majority item. So that is it really. Okay. So now this can actually be turned into the kind of algorithms that we are looking for. Okay. And this algorithm was proposed by Misra and Gries, right. And but surprisingly, it has been discovered multiple times, rediscovered multiple times independently, right, each time with a slightly different variant maybe. Okay. So here what do? Instead of keeping one item and one counter, we keep k items and k counters. We'll decide how to set the value of this k later, right. So we have k items and k counters. We first initialize all the counters to 0, right, and all the item IDs are null, say. So now I am trying to process a particular stream, a particular element of the stream x. Okay. So if x is the same as any of the items that you have in hand, and you have at most k items in hand, in that case increment the counter of this item. So each of the counters, k counters, corresponds to one of the items that you have in hand, right. And if x matches any of the items that you have in hand, increment the counter. Else x, let us say x does not match any of the existing items. But if you have space, if the number of items that you have in hand is less than k, right, then you store x, that is fairly natural. You store the item x and you associate a counter with it with the value of 1. Okay. And if none of these happens to be the case, this is the most interesting setting, right. If none of the above two happens, then we drop x first of all, but we do something strange, right. We decrement all the counters by 1. So each of the k counters is decremented by 1. Okay. So this might seem strange to you, but this is what really makes the algorithm tick. Okay. So you keep on doing this, right. And now finally, suppose at the end of the stream, somebody gives you a query q. Okay. So there is only two possible cases. The query is an item ID. Either the item ID is something that the algorithm had in hand at the end of the stream. In that case, you return the counter value associated with that item, or else you return 0, because the algorithm was not tracking this item. Okay. So let us see. So just some notation again, and I think we have already done this, but supposing, for any item x, will denote its frequency by fx. Okay. and at the end of the stream we are storing some set of elements with the associated counter values. If the query y is in hand, then f hat of y is defined as a counter value, because that is the value that you are returning, else f hat of y is defined to be 0, right. So we can sort of cast the algorithm in this way, cast the final query in this way. So just let us run down a small example. So supposing k equal to 2, right. Okay. So first you store the red with a counter value of 1, you store the blue with a counter value of 1, then red increments the counter value by 2, 3, increments the counter value to 3, then you get a turquoise. Now what do? I am only allowed to keep 2 items, right, and turquoise is not there. So I drop turquoise, but then I decrease each of them. I decrease this to 0, I decrease this to 2. Then I get a blue. I increase this to 1 because I have blue in hand. I get 2 reds. I increase this to 4. I get a blue, increase this to 2. I get again a turquoise. So again I have to drop this, right. I decrease this by 1 and I decrease this by 1. Okay. I get a yellow. I decrease this to 0, right, and I decrease this to 2. Then I get a blue. So at this point, since this is 0, you can imagine that blue is not there, that once a counter becomes 0, we could as well drop that corresponding item. But it turns out that in this example I get a blue again, right. So I add blue in with a counter value of 0, and then I get a turquoise. So this becomes 0 and this becomes 1. Okay. So that is how it is. So why is this a nice algorithm? Okay. So here is the first claim. The first claim is somewhat weaker than the final claim that we will sort of write, but it is nevertheless useful to think about it, to think about the simple question first, because it is similar to the majority question that we handled. What we will claim is that no element with frequency strictly greater than m by k is missed at the end, right. So notice what is m. So m is the length of the stream, which is also the sum of the frequencies of the elements, sum over all x belonging to the stream, right, x belonging to stream S. Okay. Because every item, every sort of copy, every ID in the item in the string corresponds to one of the, updates one of the frequencies of one of the elements, right. So it shouldn't surprise. So this statement shouldn't surprise you, right, because the argument for this is going to be exactly the charging argument that we made, right, because each decrement. So imagine what is happening in each decrement. In each decrement or a drop, we not only throw away this one element, but we are decrementing other k minus 1 elements, right, because when we throw away an element, when we are not able to add it to the list of elements that we already have, right, because we have k elements, we drop this element, right, but then we decrease the count of k other elements. Okay. So therefore each decrement, right, is charged with k arrivals, because these things because these counts must correspond to some arrival of the corresponding item somewhere in the stream. Okay. So each possible drop or each possible decrement is charged with k arrivals, but how many arrivals can there be in total? There cannot be more than m arrivals, because the length of the stream is m, right. So therefore if there is an item with frequency greater than m by k, right, I could not have dropped or decremented all the copies of this item, right, because there can be at most m by k less than equal to m by k total decrements and drops per item, right. So per item there can be less than equal to m by k decrements or drops, and therefore if the frequency of an element is strictly bigger than m by k, I must have that at the end. Okay. So this seems like an intuition, but it is really very formal. So and the statement that we can make is which is a more precise statement, is something like this, right. So, I did not want to I mean this statement seems mysterious, but it is really exactly the same thing that we discussed, right. So, now imagine that, so choose the value of k to be 1 by epsilon. Okay. Suppose f x is the frequency of the item x and f hat x is the frequency estimate. So, so remember that f hat x is either the counter value that you have in the end or it is 0. Okay. So, what we claim is that f hat x is less than equal to f x and f hat x is greater than equal to f x minus epsilon m. So, why the former? So, the fact that f hat x is less than equal to f x is easy, right, because we only sort of increase the frequency of an element when we see it in the stream. So, therefore, f hat x is at most less than equal to f x. Why is this? So, again I will not write down the formal proof of this, but the argument is exactly the same, right. So, there can be at most for the element x, there can be at most m by k deletions or drops, right. So, therefore, I mean f hat x must satisfy that f hat x is bigger than or equal to f x minus m by k, which is equal to f x minus epsilon times m. Okay. Again using exactly the same charging argument as before. Okay. So, just to summarize, I mean in this lecture we gave you a simple deterministic algorithm to estimate heavy hitters. This however works only in the rival model. This was proposed in 1982, rediscovered multiple times with modifications. Very interestingly, this algorithm also forms the basis of some recent work on matrix load anchor approximation in the streaming setting. In our next lecture, we will discuss a bunch of other algorithms. So, just to give you some reference, a lot of the slides that you see here and the examples that you see here are from the lecture slides, this excellent lecture slides by Graham Cormode. There is also some lecture notes by Amit Chakrabarty that we have pointed out yesterday, as well as a monograph by Graham that is very useful. So, thank you.